Today we will start a new topic, which is direct current circuits. And by direct current circuits, we mean circuits where the electric field generated in that circuit doesn't change direction. These are called DC circuits, if you have heard of that. And this is an abbreviation of direct current. This is in contrast to what we call AC circuits or alternative current circuits, where in this case the electric field in the circuit keeps switching directions, and so the current in the circuit accordingly keeps switching directions. Okay, so in DC circuits or direct current circuits, the electric field is always in the same direction, doesn't switch direction, and so the current also flows in a given direction. It's either clockwise or counterclockwise. But in AC, the electric field flips direction, and so the current also flips direction in the circuit. Now, this topic has some few subtitles below it, and the first subtitle is what we are going to discuss in this lecture, which is the electromotive force and resistances. Here we will introduce the idea of the concept of electromotive force and its terminal voltage, and consider R circuits. That is, we will first consider the simplest circuit, which is composed of a battery, for example, and a single resistor. We'll derive the circuit equation, and then we will consider the resistances when they are connected in given configurations that we call series configurations or parallel configurations. Some of you are familiar with this topic, I'm sure. This is the topic that we will be discussing today. Now, other topics that we will discuss also in future lectures or future videos will be the Kirchhoff's rules. That is when you have circuits a bit more complicated and we want to analyze these circuits and try to find the current in that circuit. Then there is we do this with the aid of two rules that reflect actually conservation of charge and conservation of energy, and these are called Kirchhoff's rules. So we'll see when we need to apply these rules and what are these rules, and consider examples. The third title under this topic is the circuits where capacitor. So we will include a new element now into the circuit in addition to the resistors, which are the capacitors in this course. So in this case we will have what is called RC circuits, resistor, capacitors, DC circuits. This will be the circuit in this case. We will see what is or how does the process of charging a capacitor takes place, how does the current and voltage in the circuit in this case and across the capacitor vary with time as charging takes place, and the same applies when we also discharge a capacitor. Now, RC circuits are circuits where you have a capacitor, are actually circuits that are different than R circuits here, in that the current in that case is actually not constant in time, but it actually varies with time, and we will see why does this variation takes place, and we will understand it and understand its characteristics. And of course we will talk also about energy considerations in these RC circuits, as well of course as the R circuits. So our first topic for today is just electromotive force and resistance, and we start with the simplest circuit, this circuit that we have seen before when we introduced the power in electric circuits, and it's composed of a single power source. Call it battery. This is an ideal battery in this case. By ideal, as we see that it doesn't have internal resistance. We will talk about a realistic battery just shortly. So it is a device which maintains a constant potential difference across its terminals. This longer line corresponds with the plate with higher potential, and this smaller line corresponds or represents the plate with smaller, lower potential. So this is the minus, the plus. These are the two poles, if you think of the battery or the power supply. The plus meaning the plate with higher potential, and the minus meaning the plate with lower potential. Now we assume that this battery maintains a potential difference of dV, delta V, across its terminals all the time, as far as it's functioning, as long as it's functioning. Now when you close the switch, an electric field will be set in the circuit, and this electric field will drive a current into the circuit, and this current will be in the same direction of the electric field. So the electric field here will be in this direction, here across the resistor will be from up to down, and here from down to up. So the direction of the electric field follows the direction of the current in the circuit, generally speaking. Okay. Now we have learned, when we talked about the power in the electrical circuits, we learned that the potential energy given to the charge carriers, I'm talking about positive charge carriers in this case as a convention, electric potential energy given to these charge carriers here is the same as the energy dissipated into thermal energy in the resistor. And we came to the so this is a reflection of the fact that, so if you have a potential energy q dV, for example, at some instant of time given to a charge q as it crosses these terminals, then that same amount of energy will be changed into heat as thermal energy as the same amount of charge crosses the resistor. And the meaning of this, of course, is that the potential difference between these two circuit elements are the same. Well, there's another way to say that the potential difference is actually the same, which is this. Now, this point B and this point C are the same potential. We have noted before that if there are no circuit elements between 2 points on a circuit, then these points are at the same potential. So B and C, there are no circuit elements between them, so they are at the same potential. A and D are at the same potential. So this means that VB minus VA, which is VBA, which is, we call it delta V, is the same as VC minus VD. Note that point C is at higher potential than point D, because this is, the electric field is in this direction, and so the electric field goes from higher, the electric field direction, the potential, there is a potential drop as you go along the electric field. So this point is at higher potential than this. The potential drops as you go from C to D. So delta V is just what we call E, the electromotive force. Okay, this is the nominal value of a battery, for example. This is what's written on that battery. So this is the ideal battery. This is the same as the potential difference across that battery. So this is the electromotive force. The name force is a bit misleading because there is no force there actually. This is the potential. That's just the potential. So, but this is historical name, and so still keep it. So this is delta V is the potential difference across this ideal battery with no internal resistance is just equal to the electromotive force of that battery. Noting that VB minus VA is the same as VC minus VD, then, and noting that the potential drop across a resistance is just IR, then you substitute for VC minus VD IR, and for VB minus VA you substitute E, then you get this expression, that is the potential drop here, rise here is equal to the potential drop here, or the potential across the electromotive force equal the same as potential across the resistor, and so from which you get this basic equation for the most basic circuit, which is composed of a single resistor and a single ideal electromotive force. It says that the current flowing in the circuit is just equal to the electromotive force divided by this resistor. This resistor is usually sometimes called the load resistor. The load resistor. It means the resistor that you include in the circuit and represents the resistance of the device. Okay, so usually when you want to utilize electricity, for example, to generate other source of energy, like for example a light bulb or a heater or whatever, then that device will have its own resistor, and it will act to change the electrical energy into heat or light, for example, and etc. And therefore, the resistance of that device is called the load resistance. Okay, and so this is the simplest circuit, ideal circuit, composed of an ideal battery with no internal resistance, a single load resistor, and the current in the circuit in this case will be given by E over R. And the current, the direction of the flow of the current is always, if you have a single electromotive force in the circuit, is going from the negative to the positive. Why is this? Because this is the lower potential, this is the higher potential. Inside the battery, the forces involved in the battery do work on the electric charges as they move across the battery, and so increasing their potential energy. And to do this, the charges must be moved from lower potential energy to higher potential energy in order to include potential energy into the circuit. And so this is the direction of the flow of the current in this circuit in the battery, from the negative to the positive. I'm talking about a circuit when I have a single battery in that circuit. In real batteries, we actually have internal resistance of the battery. So look at this figure now here. In this figure, you can see a real battery. The real battery is this, which we call the electromotive force, and there is an internal resistance. We refer to it with small r to distinguish it from the load resistance. This whole thing, which is put inside the box, is the battery in this case. Okay, is the real battery, and this is the internal resistor of the battery. Now, the terminal voltage in this case in the battery is different than the electromotive force. Okay, the terminal voltage of the battery is the potential difference between point D here and point A here. Okay, it's not between B and A. This is the electromotive force. It is between D and A, and in this case, this potential difference, or this terminal voltage or terminal potential of the battery, is delta V, which is the potential difference between D and A in this case, is equal E minus IR. Why is this so? Well, because the potential difference between A and B, A and D, is now the potential difference across this plus the potential difference across this. But with the current flowing this direction, this point is at higher potential than this point. This is just a resistor, and the current is flowing through it. So the current is flowing through a potential drop. So the potential difference between this point and this point is minus IR. This point is at a lower potential than this. So the potential between A and D is the potential across this, which is E, plus the potential across this, VD minus VC, which is minus IR. Potential D is at lower potential with respect to C. So VD minus VC, which is delta V, the potential difference across the battery, is minus I. The resistor, internal resistor, is just minus IR in this case. Okay, so this is the terminal voltage of any battery. It's always E minus IR. Delta V, of course, the terminal voltage is equal to the electromotive force only when I is equal to 0. That's when you have an open circuit. In this case, then if you measure the potential across that battery, then it will be the value written on that battery. In real circuit, when it's operating, actually the potential difference is across the battery is actually this. It's less than the electromotive force written on the battery. Now, let's analyze, let's find the expression for the fundamental equation for the circuit that contains a real battery, that's electromotive force plus internal resistance, and a single load resistance. Again, point A and point F are the same potential, point D and point E are the same potential. So VD minus VE is equal to VD minus VA, VD minus VA is equal to VE minus VF, VE minus VF. Note that E now is at higher potential with respect to F, because this is how the current flows. And if you substitute for VE minus VF IR, and you substitute for VD minus VE, just E minus IR, equate IR to E minus IR, then this is, take this to the other side. Okay, so IR equals E minus IR, take R, I'm sorry, there is a small r. This should be small r, and here it's corrected. So take this to the other side, you get E equals I capital R plus I small r coming from this here. So this is the basic equation, the circuit equation in this case. It says that the electromotive force is equal IR plus I times small r, and so the current in the circuit in this case will be just the electromotive force divided by the sum of the load resistor R plus the internal resistor R. So the only difference between this circuit equation and the one that we have derived earlier for the ideal electromotive force is in the appearance of the load, the internal resistance of the battery or the electromotive force source in the denominator. Now, if we talk about power in this case, then if we just multiply this equation by I, then this becomes I, multiply this equation by I. If you multiply this equation by I, then you get this equation. But what is IE? We have seen before that this is just the power delivered by the battery, which is the amount of energy per unit time that is delivered, electrical potential energy delivered by the battery to the circuit. What is I square capital R? This is the thermal power dissipated in the load resistance. And I square small r, the thermal power dissipated in R, and how much energy, thermal energy per unit time is dissipated in the internal resistance. So what is this saying at you? This circuit equation is actually nothing, but it's, as such, it's a reflection of conservation of energy, because the power delivered by the circuit, where does it go? In the steady state, when the circuit is operating, it goes into thermal energy dissipated, or thermal power dissipated in the load and in the internal resistance, and they should be equal to conserve energy, assuming that no other this electrical energy does not get transferred to any other form of energy in any other circuit elements. I mean, there are no other circuit elements to consume this power. So this is conservation of energy, and the basic equation, the basic circuit equation, is just a reflection of conservation of energy. We will come to this point later when we consider the Kirchhoff's loop rules, actually. So that's it. Actually, here we can plot the circuit equation, this circuit equation here. Okay, or yeah, we can understand it here on this graph. This graph here on the positive, on the vertical axis, you have the potential, and in the horizontal axis, you have the points on the circuit. So, for corresponding points in the circuit. So, point A, for example, here, we start from point A and we assume the potential of point A to be 0. Now, when you move from A to B here, the potential jumps to E, because you have electromotive force. Okay, so the potential from here to here goes to E. Now it's maintained B and C are the same potential because there is no circuit elements between them. Now between C and D, there is a potential drop because you are moving through a resistor in the same direction of the current, and in the same direction of the electric field. So there is a potential drop here. Okay, and this potential drop is equal minus IR, so it goes down by IR. Then there is no potential difference between this D and E, as you can see here. So the potential of D and the potential at E is the same. Then between E and F, as you go across the load resistance, then the potential drops again. And it comes to, the potential becomes the potential of point F. But point F and point A are at the same potential. So we assumed A is at 0 potential, so this comes back at 0 potential. So what it says here is that it says that the potential rise across this is equal to the sum of the potential drop across this and this. This is what does this say. Okay, we will come back to this and later. But this actually, this thing that the potential rise through this is equal to the potential sum of the potential drop across this and the potential drop across this, when viewed here, it says the following. It says, because it is this, E, the potential rise across this, is equal to the potential drop across this plus the potential drop across this. So this is a potential rise equals the potential drop here, the potential drop here, because these are taken to the right-hand side. If you put them at the left-hand side, E minus IR minus I capital R minus IR small r equals 0. So what does it say actually when we multiply this by I? As we have noted, it is this. What does this say is why this should be so. The potential rise across E should be equal to the potential drop across small r, the internal resistance plus the load resistance, because this is just a reflection of the fact that the power delivered, the electric power delivered by the circuit, by the battery or the electromotive force, should be consumed exclusively by the load resistance and the internal resistance as a manifestation of the conservation energy. It doesn't go anywhere. If these are the only types of energies present in the system, then all the energy that is provided by the electromotive force as electric potential energy, this is consumed and changed into thermal energy by these two circuit elements. So actually the basic circuit equation, which is reflected in this figure, saying that the potential rise across the electromotive force is equal to the potential drop across this plus the potential drop across this, is actually a manifestation of the conservation of energy. Now this is very, very basic, and this is very important. And these energy considerations actually underline conservation, they underline many of the relations that one derives when one does circuit analysis, even in more advanced techniques. At the bottom of them, you will always have conservation of charge and conservation of energy. Okay? These you might encounter in other courses in the future, but if you go look deep down, in most cases, this is what underlines these different relations. We will come to these when we consider Kirchhoff's rules, and it will be one of Kirchhoff's rules, but here I have explained actually the basis of that, the physical basis of that rule. So having done this, you are ready to do a checkpoint. This is a very simple checkpoint that you can readily do. Now it's time for an example, and the example that we will discuss in this case, this is a very simple example. It's a straightforward application, and it says that we have a battery. The electromotive force is given 12 volts, and it has an internal resistance which is 0.05 ohms. Usually it's small for a reason that we will see now, and its terminals are connected to the load resistance, which is 3 ohm. So this might be, for example, a light bulb, a small light bulb connected to a resistor. 12 volt resistor is a typical resistor that you use in your everyday use. You can see these batteries, for example. So what we want to find the current in the circuit, and we want to find the terminal voltage of the across the battery. The current is obvious. The terminal voltage is VD minus VA. So let's start with the current. The basic equation, circuit equation, is E divided by R plus small r, and you just substitute, you get the current is 3.93 near 4. Now what is the terminal voltage? Well, the terminal voltage is E, electromotive force, minus I times the small resistance, or the internal resistance, small r. Okay? So you just substitute this straightforward, and you get it is 11.8 volts. So note that electromotive force is 12 volts. This is what's written on the battery, but when it's operational, the battery in operational, it is 11.8 volts. And what determines the potential or the voltage across the battery when it's operational in a circuit is not only its small internal resistance, but it's the load resistance, because the load resistance, as you can see here, governs what is the current, and this current determines what is the terminal voltage of the battery. Okay, so that's what. Note that here as a point of check, we can check that the terminal voltage is the same as the potential across the resistance, the load resistance. It is this. Again, manifestation of conservation of energy. What is the power delivered to the load resistance, the power delivered to the internal resistance, and the power delivered by the battery? By the battery. So the battery is the source of electric power. The others are the consumers. So just we apply the relations. Power to the load is I square R. It's 46 watts. power consumed in the internal resistance is just 0.7072 watts. We usually need this to be small because, I mean, we don't want this first to heat up. And the second thing, we want the electromotive force to deliver power to the load, not to itself. Okay, so this is why we take it to be small, and it is 0.77 watt, and their sum is 47.1 watt. Now, if you multiply E, the load, the electromotive force, with the current in the circle, which is 3.93, that's IE, you must get 47.1 watt. You can check. Okay. Now, to continue, we say that as the battery ages, it's known that the internal resistance of the battery increases. So suppose, for example, that for our battery, the internal resistance of our battery changed from, or increased from 0.05 to 2 ohm, okay, towards the end of its useful life. How does that alter the battery's ability to deliver energy? Okay, let's check. Well, it's evident from here that in this case you substitute for small r 2, and so the current drops, the current in the battery drops from 3.943, so it's about near 4 amperes, to 2.4 amperes. And of course, the meaning of that is that the terminal voltage also drops to 7.2, so it was like 11.8, you remember? Now it's dropping to 7.2, and so the power delivered to the load drops from 46 something to 17.3 watt, which is very, very low. And this is comparable to the power consumed by the internal resistance in this case. So in this case, the battery, of course, starts to get really useless in that it's not delivering sufficient power to the load resistance, and it's heating up very quickly in this case because a large amount of power is delivered to the internal resistance of the battery.